Good afternoon, everyone. Welcome to the eighth session on chemical engineering thermodynamics problem solving session. Today, the topic is on thermodynamics of mixtures. The course instructor is Professor Shashidhar Guma from IIT Tirupati, and I am Namrata Kulkarni, PMR scholar from IIT Madras. So till now we have learned initially what are the fundamental property relations here. These fundamental property relations for a closed system. And in the last week, we have discussed for an open system, not only with respect to pressure, this any molar property changes with the composition of the mixture also. So here T, P and Xi or Yi, the composition, all these three play an important role in determining any molar property. So similarly, the derivations for the Gibbs energy, enthalpy, and also this is entropy and volume. So we have got expressions for all the molar properties. And later we discussed what are the partial properties. So there are three distinct types of properties we can discuss as shown here. One is the, like for example, I have a pure species 1, okay? And I have pure species 2, where it is cross. So I have a mixture of these two species. Okay, the property in this is M. Then property of 1 is M1 bar, and this has a property of M2 bar. Whereas here it is M1 and M2. So this is the one we have discussed earlier and how they can be related. So for the overall property of a mixture, it is summation of Xi into Mi bar. It is not Xi into Mi, but Mi bar is defined. So how this Mi bar is derived and all, we should be discussing and all. Yeah. So coming to the like generally we have discussed earlier also that for a pure species, for a gas or for liquid, for a pure species, there are different kind of models like ideal gas, Redlich-Kwong, and so Redlich-Kwong, Peng-Robinson, sorry, yeah. All these we have discussed. So similarly, for the mixtures also, we have different kind of equation of state. Okay. So like that, we'll be discussing different things. Generally, here we are having molar property of mixture M. Mi bar is partial molar property of component I in the mixture. And this is property of pure component type at the same T and P. So ideal gas state mixture. So now we have gases, liquids. So like generally we know ideal gas for law also, right? PV is equal to RT. Similarly, we have ideal solution also, okay? It's ideal gas mixture. And this also follows PV is equal to RT and ideal solution is also there similarly. Okay, we'll be discussing about that in later sessions. Now today we are going to discuss about the ideal gas mixture model. So this is mostly valid in the limit of zero pressure, and this can be considered for so many systems because it has a molecular basis. It defines system on like it assumes zero volume for the molecules, and it assumes no interaction among the molecules. That are the only assumptions here. So it is developed based on the molecular system, and it is very analytically simple. Okay, so here we say for an ideal gas mixture, the V is RT by P. So the mixture at temperature and pressure T and P. Okay, and for each thing we have VI, IG bar. Okay, this is MI bar. And it is IG, ideal gas model, right? So that's why we are putting ideal gas. So later we will be discussing other models. That's why we have a subscript IG here as a, like we will be using this model as a reference and other models for usage, and we use a property like M residual is equal to M minus M IG. Okay, it means like how much is it deviating from the ideal gas mixture model. That is given by residual model. Okay, we'll be defining this later. So that's why we are using an superscript here. Okay, so now VIIG bar is defined as dou NVIG by dou Ni. Okay, on differentiating this with respect to Ni, then we will be getting same RT by P, right? So that's why VIIG bar is equal to VIIG here. Okay, it is equal to the pure I. And this is I in mixture. Okay. So last week we have learned that M is equal to total molar property is equal to summation of this molar fraction into Mi bar. I have shown this here, right? Xi Mi bar. This one is used here also, but since it's a gas mixture, we have Yi. This is also molar fraction. So that gives us V of Ig at T and P. This is for the mixture is equal to, this is I in mixture. Okay, Yi into this. And this is equal to pure thing. So pure I. Right? So here we can define delta V mixture in ideal gas model equals to 0. Okay. Right. So here, using this molar fraction, we define a partial pressure which is equal to RT by VIG into Yi. Okay, this YIP. And this sigma Yi equals to 1. And also, one has to know that here, as I said, for example, this is one molecule, blue color, and another one, this red cross. This VIIG bar is the So this species has a pressure of Pi, okay, which is equals to YIP. So VIIG bar is similar to equals to VIIG at TI. Okay. So this VIIG bar is defined at the temperature T and pressure P, which is the overall pressure. But it is taken as it is equal to the molar property of the pure species at Pi in the ideal gas model, right? So this is understood first thing, and this is also understood. Right? So we have done this for the volume here. Later, for the other things, we know that as the pressure is very going to tends to 0, and in the ideal gas mixture model, the enthalpy and entropy are independent of pressure. So that's why we know this MIIG bar at T comma P equals to at T comma Pi, right? So we can almost say MIIG bar equals to MIIG at T and P for H and S. So that's why this is defined at T and P only, not T and Pi, because anything is same for enthalpy and entropy. Okay. So now we have this ds ds is equal to Cp dt minus dou v by dou t into Tp at constant P, right? So at a constant temperature, if I define this is 0, so ds by at Ig is equal to minus R d ln P. Okay. So that's why SIIG at T and P minus SIIG at T and Pi is equal to minus RD. Sorry, yeah, if it is integrated, minus R and then P by Pn, which is R ln Yi. So I have SI Ig bar equals to SIIG at T comma P I. So Pi, right? So here what is Pi? So this is equal to SiIG at T comma P minus R ln yi. So this is here inserted here. Okay, so this is how we get this equation. The next equation is GIIG bar. So we know GIIG bar equals to HIIG bar minus TSIIG bar. By inserting things here, HIIG minus TSIIG minus R ln yi. Okay. This is all are defined at T comma P. So that's how I get this equation. So later we have discussed this right already. It's a summation of things. For the volume also we have done. So resultant we get H of, this is the property of mixture and this is the property of purine. So we don't know what is Mi bar in a mixture. Okay. So that we are expressing in terms of Mi, which is the pure thing. So we know the values of pure species, and when it is in a mixture, how is it, what will be the overall property of the mixture that we want to know. So what all parameters it can depend on is, like here we see this enthalpy is dependent on the mole fraction. Okay, and this entropy is dependent on mole fraction only. Whereas coming to this, the Gibbs energy depends on temperature and also mole fraction. Okay, fine. Now, coming to that, the Gibbs energy thing can be described in a different way also, because we know dG equals to VdP minus SdT. At constant temperature, GT is equal to 0. So, dGIIG for the pure species, I can say, is equal to VIIG dP equals to RT by P dP equal to RT ln P. On integration, I will get GIIG equals to some integration constant, which is a function of temperature. Okay, so this was excluded, right? Generally, G is a function of T and P here, but we have excluded this property, this thing. So at constant T, so this should be used here, right? So that constant is dependent on temperature and plus RT ln P. This was D ln P. Fine. So this is derived here. Earlier also it was the similar, but here it was summation of like it's only dependent on this temperature and yi. But here I'm writing it in terms of temperature, pressure, and yi. This P, if it is going into a mixture, the same thing can be described as YIP. Okay, RT ln YIP. This P will become PI, right? Inside the mixture. So that's how I'm defining this GIIG bar. Now, this is I in mixture. This is pure I. This is for the mixture. GIG equals to sigma yi into Gi bar, right? So from that we get yi tau it plus rt sigma yi ln yip. So this is that. So now what we want to define is if some other model I'm using by removing the assumptions of no volume, no interaction, these kind of things, what will be my properties? The Gibbs or enthalpy or entropy or volume. Okay. Like I explained in previous sessions, if volume, for example, I have added two liquids of okay, two gases only. I don't want to deviate. So two gases which has 1 meter cube volume, but upon adding, if they are if the molecules are attracting each other, they have van der Waals forces or something like that, then the volume of the whole system will be decreased. It won't be 2. It will be somewhat 1.7, 1.8 like that, meter cube. So that is accounted in different models. Okay, ideal gas mixture won't account that thing. That's why we have delta V mixture is 0 in the ideal gas, right? So, okay, I want to make a note of those things. Hmm. I want to erase it here. Okay. So delta V mixture in Ig is equal to 0. Delta H mixture in Ig equals to 0. But coming to delta S mixture in Ig equals to Si, sorry, Sig minus sigma Yi Sig. This is defined like this, okay? Equals to R sigma Yi ln Yi. And the next one is delta G mixture Ig equals to RT sigma Yi ln Yi. Okay, so please make note of this. Now coming to the analogous thing, that what I said, model deviating model which is able to describe deviating from ideality. Okay, so in that, the analogously the G to I this gamma I plus RT ln P is there now. This will be ln Fi now here at constant temperature, right? And this is for the pure species. And this is I in mixture. Okay. And again, you know how this M is equal to sigma xi Ci back. This you know, right? Xi or Mi for gases. Okay. Right, so this is the fugacity we say, which has a units of pressure here, similar to this equation for an ideal gas. And in the mixture, it is represented by phi hat. Okay, this is the fugacity of species I in the mixture, which is same as YIP in an ideal gas mixture, like this. Now I define residual property. This residual property is defined for gases, whereas excess property is defined for liquid solutions. Okay, so GI minus GIIG, GIR is defined as RT FIP. FI by P, okay, and here this is phi. So this minus this we are doing, and that's how we are getting Fi by P. So that's why we have fugacity coefficient. So it is pressure by pressure, right? This has pressure units both. So this is dimension plus number. And similarly for the mixture thing, how much is it deviating from an ideal mixture? The residue property is defined, and we have phi I hat there. Okay, so this is all what has been discussed by Guma sir in the week 8 classes. Now we'll just pick up few questions and go through them. Okay. For an ideal gas, the entropy change of mixing depends on. So as I said, delta entropy. Okay. Entropy for mixture ideal gas equals to R sigma Yi ln Yi. So it only depends on the mole fraction, the composition of the mixture. Now, the Gibbs energy change of mixing depends on what? Delta G mixture Ig equals to RT sigma Yi ln Yi, right? So it depends on the temperature and composition of the mixture. Now, the binary mixture is prepared by mixing 100 moles of each of two ideal gases. So 100 moles of each. So N1 is equal to 100, N2 is equal to 100. So these are gases, right? So Y1 is equal to 0.5 and Y2 equals to 0.5. Okay, the entropy change. The entropy change of mixing, the delta S mix Ig equals to R into sigma of, right? So 0.5 ln 0.5 Yi ln Yi, right? Plus 0.5 ln 0.5. So this is equal to his here, this here. R into ln 0.5, 0.5 plus 0.5, 1, right? A ternary mixture is prepared by mixing 100 moles of each. The Gibbs change energy of this will be delta G mixture Ig equals to RT sigma Yi ln Yi. So it will be RT, the sigma Yi 0.5, right? As we see in the last question. So this will be ln 0.5. And notice, this should be in Kelvin. And this is R8.31. Okay, fine. Now, 0.75 meter cube of CO2 and 0.25 meter cube of N2, each at 1 bar and 25 degrees, are blended to form a gas mixture at the same condition. If CO2 and N2 are having and like ideal gases at this condition, change in entropy is equal to the delta H mixture for ideal gases equals to 0, right? We have discussed earlier. So that's why this is 0. The fugacity of species I in an ideal gas mixture equals to. So we have discussed Fi is for pure species. And Fi hat is for I in mixture. Right? So here we are been asked the fugacity of species I in an ideal gas mixture is this Fi hat, and this is equal to Yip in ideal, and this is P in ideal. So it's partial pressure. It's equal to Pi, right? That's fugacity coefficient of species I in a solution. So one thing. So what phi I told was for the gases. But for solution also we express the same. So for gases, how do we define Fi by P, right? Or in a mixture, Fi hat by Yip. Similarly, for liquids also we define the same. So it has no dimension, right? Okay. Now, as pressure approaches 0, the ratio of fugacity to pressure for a gas approaches. So, the first thing is you might be thinking F by P, so pressure tends to 0. But this doesn't tends to infinity because this also F also becomes equals to P here. When pressure tends to 0, it behaves as an ideal gas system, right? That's why it will be going to unity. So this was a very simple thing till now. So this week we have just took very simple questions out of this thing. So later we will be discussing the next week's sessions. Thank you for today.